Bonjour à toutes et à tous, je vous emmène.
Hello everyone, today I'm taking you to one of the world leaders in embedded intelligence. It is a French company of the Safran group called Safran Electronics and Defense, and we are here at the Eragny-sur-Oise Research Centre in the region of Paris.
Eragny-sur-Oise en région parisienne. Alors c'est quoi l'intelligence embarquée? Eh bien, pour résumer...
So what is embedded intelligence? Well, to sum up, these are high-tech electronic systems and equipment which allow planes, submarines or launchers such as the latest Ariane 6 to navigate reliably, safely and even independently. Let's go.
Sûr et même en toute autonomie. C'est parti. À propos d'autonomie, on va s'intéresser tout particulièrement.
Regarding autonomy, we are going to focus on inertial navigation systems during this program. An inertial system is a navigation instrument which makes it possible to locate oneself at any time with great precision without using external information such as GPS. These IMU have many uses in the civilian field but also in the military sector, so for granted access here, one must be fully authorized.
Patte blanche.
Imagine a nuclear submarine that must travel thousands of kilometers discreetly without ever rising to the surface, or a fighter plane navigation system of which must not be jammed by the adversary. In both cases, it's impossible to use a GPS. It's far too easy to jam and sometimes simply unavailable. The solution to combine safety and autonomy is to use an inertial navigation system. But how does it work? And what precision can it achieve? To find out, let's head to Safran's research laboratories in Eragny. We will also visit the factories in Mont-Luçon, where inertial navigation production involves ultra-modern technology. Of course, it took time to reach this level of sophistication. We will be tracing the history from the first navigation tools to the latest innovations. Let's not waste another minute and head for Eragny.
That is the program for today. However, before we take you behind the scenes of these research labs, I suggest you discover the operating principle of an inertial navigation system. We're going to take an example of a submarine and you're going to understand everything.
Tell me, it seems that apparently submarines don't use GPS. Is that true?
This is true for some submarines, which must be completely undetectable. This is why they travel underwater for several months without ever rising to the surface. During this period, they do not communicate with the outside world to locate their position. GPS waves don't go through water anyway, much like driving a car through a tunnel.
Well, how do they know their position?
In fact, submarines use navigation equipment such as this one. This instrument is able to precisely define the position and orientation of the vessel at any time and without any outside assistance. This is called an inertial navigation system. And to understand how it works, I suggest you climb on board. Departing Brest, destination Toulon.
Aye aye, Captain. Heading south.
Not so fast. Because you have to find the initial orientation of the ship and precisely define the starting point, this first step is called alignment. It's a bit like when you go hiking. You align your map with the external reality to know your position. To do this, you start by placing your map horizontally. It's easier to match the landscape elements. Then, you look for the north with your compass to orient the map. The procedure is the same with an inertial navigation system, but instead of the compass, there are sensors. Some of them determine the horizontality, while others find the direction of the north. Now all that we need to do is to enter the exact coordinates of our starting point using a map. In our case, it's the port of Brest. Now we are ready to go.
Okay, and what happens after the sub leaves the port?
Once at sea, the submarine can move up or down. This is the pitch motion. It steers sideways. This is the yaw movement, and the rolling clockwise motion. All these movements correspond to the rotation of the vessel around 3 fictitious axes represented in this way. By determining the position of the submarine on each of these axes, it is possible to know the orientation of the ship. This is called the attitude of the vessel.
Does the inertial navigation system take care of that?
Yes, or more exactly, the sensors installed in the inertial system. Some continuously calculate the orientation of the vessel. They are called gyroscopes. There are 3, one for each direction. These gyroscopes measure the angle of rotation of the vessel in different ways. For example, our submarine tilted 30 degrees downwards and 5 degrees on the right.
The submarine doesn't just rotate, it moves too.
Exactly. This is why, at the same time, we have to measure the movements. For this, there are other sensors installed in the Inertial Navigation system. They are called accelerometers. As you can guess, they measure accelerations. This is what you feel in the car, for instance, when you brake hard or turn into a bend. It's the same with a submarine. As soon as it increases or decreases its speed, for example, it accelerates. The inertial system is equipped with 3 accelerometers to measure acceleration in each direction.
And then?
Once the value of the acceleration is known, computers calculate the speed and distance continuously traveled.
Okay, but I still don't know where we are. So how do we get to that?
Let us take the example of walking again. From the starting point, if you know the number of steps, their length, and the direction in which you have walked at each moment, then you are able to trace the path traveled to your current position. The same principle applies to the inertial navigation system. The information collected by accelerometers and gyroscopes is analyzed and then combined by computers. They calculate the ship's accelerations and rotations in real time. Then they deduce the orientation, the speed, and finally the exact position of the submarine.
Okay, so if I understood correctly, it's impossible to lose the north with an inertial system.
So we have just understood the operating principle of an inertial navigation system, but there are different models and very different technologies in fact.
One of the first technologies that we recognize is the mechanical gyroscope.
Yeah, meaning only mechanical parts.
Exactly, only mechanical parts.
How many parts are there, for example?
Counting only the mechanical pieces, there are more than 500 parts.
Okay, this is integrated in a bigger case.
Exactly, with electronics encasing it. Electronics have also evolved over time. Here we have conventional electronics available at that time.
Then, moving on with technological evolution, this is a completely different technology. Here, we use lasers.
Exactly so. The ring laser gyroscope is a real breakthrough. It's much simpler with about 50 pieces.
Okay.
So, it's an optical technology accompanied with electronic evolution. Back then, the maintenance was performed mechanically. Now, with the optical laser technology combined with electronic evolution, the maintenance is performed electronically.
Does that mean it takes up less space too?
Of course, it's a processor, so it takes up much less space, and electronics also require less maintenance.
Okay, if we compare the performance between the two, what can we say?
In general navigation, you know that performance is expressed in nautical miles.
Remind us what a nautical mile is?
1,852 meters.
1,852 meters, okay.
And so overall, a system like that could be automatically efficient for approximately 8 hours.
8 hours, meaning an error of 1,800 meters over 8 hours.
Exactly, about 8 hours. And then afterwards, we have to find a way to adjust it.
Okay.
Gyroscopes have reached a new level thanks to the ring laser gyroscope, with 1 nautical mile in a few days.
Okay.
This is associated specifically with the arrival of nuclear submarines that need to dive longer, thus having greater autonomy.
Now, let's discover the latest technology.
Exactly.
HRG.
Precisely.
What does it mean?
It means hemispherical resonator gyroscope.
Okay, the sensors inside are very tiny, even minuscule.
They are much smaller, actually. They only have 3 pieces, as you can see. We started with 500 pieces for the mechanics, then 50 for the gyro-optics, and finally, we ended up with 3 HRG pieces.
Is it more powerful?
It is more powerful and much more reliable. Production is also achievable in larger quantities, since it is even easier to manufacture. On the other hand, it requires extremely meticulous processes.
So, Emmanuel, let's take a concrete example of a nuclear missile submarine that lurks in the ocean, usually for several months, sometimes 6 months. Does the inertial unit allow you to remain autonomous for several months, or do you have to go back up to update information at some point?
It's top secret, but in any case, it is sovereignty. It is totally autonomous.
So it will remain a mystery for us anyway.
Yes, even for you too. Sorry, Fred.
Okay. So we'll talk about HRG in more detail later on. But to fully understand the evolution of our navigation instruments over time and place them in a historical context, we are going to take a step back. Let's go.
Men have always sought to move from point A to point B, whether on land, at sea, or more recently, in the air and in space. But in the 2nd century BC, GPS didn't exist. To navigate, the big challenge is to know where we are and where we're going. So the sailors found their way thanks to the stars, the sun, and the moon. First with the astrolabe, that made it possible to measure the height of the sun in relation to the horizon and deduce the latitude and the time. It was called weighing the sun. Then, in the Middle Ages, the Vikings used the sunstone to locate the sun on overcast days. Much later, the first navigation instruments were developed, such as the compass. In the 12th century, it was a real revolution because it made it possible to know the direction of the ship, whatever the weather. But it was not completely mastered. And for calculating the speed, it is estimated and deduced by the navigator. This is the beginning of dead reckoning. Then, in the 16th century, the ship log appeared. It is made of a triangular piece of wood tied at the end of a long string. Once launched at the bow of the ship, it was necessary to count the time taken by this piece of wood to reach the back of the boat. The speed of the ship could then be calculated. Long before the 16th century, navigators already used the coordinates expressed by latitude and longitude to know their position. To determine the latitude, that is, how many degrees we are above or below the equator, is not problematic. For that, the navigators used the stars, which made it possible to measure the latitude directly without needing previous measurement. That's celestial navigation. Little by little, astronomical instruments were perfected. They stemmed from the astrolabe like Jacob's staff from the 14th to the 15th century, then Davis' quadrant at the end of the 16th century, which is a little more practical and precise, and finally the sextants in the 18th century, which is even more accurate. But to derive the longitude, that is to say how many degrees east or west of Greenwich meridian, is more complicated. In 1714, the British Parliament proposed to offer a prize to those who discover the secret of longitude by developing a chronometer for navigation. In 1760, after more than 40 years of work, an English watchmaker, John Harrison, succeeded in building the very high-precision H4 watch. Thanks to its high precision, even after several days of navigation, it serves as a reference for sailors to determine their position. The problem of longitude at sea is finally solved. In 1951, the French scientist Léon Foucault carried out a very famous Foucault pendulum experiment to demonstrate the rotation of the Earth, but it was not convincing enough. The following year, in 1852, Léon Foucault, with the help of engineer Paul-Gustave Froment, presented a device capable of maintaining a rapid rotation for 10 minutes, enough time to demonstrate the Earth's rotation. Moreover, this device remains perfectly fixed in relation to the stars, unlike the pendulum. He then named it gyroscope. Léon Foucault realizes that his device, once aligned with the meridian, keeps its axis oriented towards the north. The usage of gyroscope to indicate the north seemed to have solved the problem. However, it will take more than 50 years to achieve operational equipment. This work, carried out by Dr. Hermann Anschutz-Kampfer and his cousin Max Schuller, led to the first patent for a gyrocompass in 1904, the year gyrocompass was born. In World War II, during the development of V-2 ballistic missiles by the Germans, the idea came from using gyroscopes not only to find north, but also to measure speed. This is the beginning of inertial navigation. From 1950, the mastery of technologies for the production of gyroscope and accelerometer further developed. Their precision improved, and the United States played a leading role in the development of inertial technologies including Atlas, Titan, intercontinental ballistic missiles, transcontinental flights in 1953, and the Nautilus expedition under the frozen Arctic Sea to the North Pole in 1958. In France, a company called SAGEM, Société d'Application Générale d'Électricité et de la Mécanique, developed inertial technologies for the exploration of the seabed, sky, and space with impressive progress. The first inertial unit weighed approximately 500 kilos, and SAGEM inertial system weighed only 20. These gyrometers and accelerometer contributed to the success of the first Diamond rocket launch in 1965, the first Concorde flight in 1969, and the deterrent force. The invention of the laser in the 1960s allowed the emergence of a new generation of gyroscopes. In the 1970s, the ring laser gyroscope and fiber optic gyroscope. In 1978, Boeing decided to equip its planes with ring laser inertial navigation system. They were then adopted on practically all types of civil and military airplanes and helicopters. And even though in 1973 the United States launched their famous GPS, Global Positioning System, the inertial navigation system remained useful and promising because of its insensitive to interference and jamming. In addition, it provides information on the attitude of the machine, which is not available on GPS receivers. Inertial navigation and GPS are therefore in reality more complementary than competitors. From 1980, gyro-stabilized platforms and gimbals resulted in inertial systems without the platform. In fact, the accelerometers and fiber optic gyroscopes are directly attached to the structure of the vehicle, otherwise known as strap-down inertial navigation system. This new step led to real simplification of the inertial navigation system. Finally, the ring laser gyroscope established itself in the 1990s as an alternative to the mechanical gyroscope due to its reliability and low cost. Finally, the hemispherical resonator gyroscope technology was evolving with extremely low cost and very high performance. It was increasingly seen as a technology of the future.
We are still in the research laboratories of Safran Electronics and Defense, and I am with Philippe. Hello, Philippe.
Hello, Fred.
So we're going to do a little live demonstration with an inertial navigation system.
So this is a real HRG-based inertial technology that contains 3 gyroscopes, one for each axis and 3 accelerometers. The screen will show the movements of the inertial system. So if we do a yaw motion,
This side-to-side yaw motion is captured by one of the gyros as we see on the screen.
yes, and if we do a pitching motion,
We can also see that there is another gyro sensing the movements.
there you go. And if we roll,
We also have information from the third movement.
so we measured the rotations in 3 axes.
We have gyroscopes and we also have accelerometers. We will try to simply explain how it works. Philippe, let's take an example of a ring laser gyroscope that we saw earlier. So how does it work? What's the basic principle?
The ring laser gyroscope is based on the principle of a laser propagation in an optical cavity. We produce photons here, then send an electrical impulse. The photons travel in 2 opposite directions, normally arriving at the same time at the exit point.
That is when the object does not move.
Yes, the photons travel at the same speed and same distance to arrive at the same time. Now, if we turn the gyroscope, there is one of the 2 photons which has less distance to travel than the other, so it will arrive earlier. Therefore, by measuring the delay of a photon in relation to the other, we can collect the rotation information of how much the gyroscope has turned.
This is for gyroscopes. Now, the accelerometers which, as the name suggests, measure acceleration. So there we have 3 different models depending on the year, right, Philippe?
Indeed, here we have a slightly older model.
The one that we will find on this inertial system.
Precisely. That's the inertial navigation in the 80s. Here we have a slightly more recent model from the early 2000s. And here we have the current generation that is even more miniaturized.
It's really, really tiny. And in fact, to fully understand the principle, you made us a 3D model of this mini accelerometer.
This 3D model refers to the sensitive element contained in this small box, which is made up of 2 silicone plates. One of these plates was cut in order to constitute a pendulum, with this mass in the middle that is attached to a small flexible hinge. When we apply an acceleration to this object, we can see that the heavy mass goes downwards. And if I accelerate with my hand, we see that the mass follows the movement applied. And thus, by measuring the relative movement of this mass compared to the external plate, we can obtain the information of acceleration.
And these various instruments are developed here?
Absolutely.
Then let's take a closer look. Philippe, how long does it take on average to develop a sensor, whether it's a gyroscope or an accelerometer?
It takes about 10 years. Initially, we make the first prototype. If we are not fully satisfied with it, then we will improve it, make a new generation of the prototype, and we start over several times until we reach the desired performance.
And it requires a variety of complementary professional skills, in fact.
Absolutely, yes. For example, for ring laser gyro, we are going to need physicists specializing in laser physics. For the new microsensors, we will need thin layers specialists, for example. And then, of course, we will also need electrotechnicians to precisely measure these small currents supplied by the sensors.
Yes, of course.
We also need software processing technicians in order to be able to use the information provided by the sensors in a precise way, and then develop an elaborated navigation from that.
In addition, you have sensors with completely different technologies, so you have to relearn the job every time.
Exactly. Each new generation is not an improvement on the previous one. You really have to start all over again and master new skills each time. This is also the reason why it takes time.
All these jobs are fortunately open to both men and women, as we saw in the laboratories, and it's important right now.
Of course.
Especially in the science and technology sector, we must continue on progressing.
Continue.
Let's focus on the gyroscope family, the HRG. It is based on another physical principle than the ring laser gyro, and its performance is even better. You're going to understand how it works.
Vous allez comprendre comment ça marche.
Can you remind me what a gyroscope is?
A gyroscope is an instrument that measures an angle of rotation when installed on a boat, an airplane, or even a submarine. It indicates the orientation of the vehicle in space. There are several types of gyros, but the most compact and most economical is the hemispherical resonator gyroscope, or HRG.
I bet you have a logical drawing to show me how it works.
I've got even better. Let's do an experiment to understand the physical principle behind this gyroscope works. Let's take an object and hang it on the end of a long cable attached to a high ceiling. When the mass is in motion, it goes back and forth regularly. Now let's place some marks on the ground. After a while, the mass no longer passes in the same place. Its trajectory seems to deviate slowly.
That's weird. There's no wind.
In fact, the mass always oscillates in the same plane, but it is driven by the rotation of the Earth. We can say that the plane of oscillation is inertial. By measuring the position of this plane relative to fixed marks on the ground, we can calculate the angle of the Earth's rotation over time. This experiment highlights the principle of inertia, and was performed for the first time by a French physician, Léon Foucault, at the Pantheon in the 19th century.
Incredible! But there is no Foucault pendulum in the gyroscope.
No. It is replaced by a small glass bowl covered with a thin layer of metal. It is called the resonator. It follows Foucault's pendulum principle of inertia like the mass. When this bowl is stimulated by an electrical impulse, it begins to resonate. In other words, it vibrates by deforming itself successively in two perpendicular directions. These two axes remain almost always oriented in the same way. This is called the orientation of vibration. Look, if the bowl is turned, this initial orientation is maintained, regardless of the rotations of the base platform.
What are the marks placed on the ground in the experiment replaced by?
These marks are replaced by several electrodes installed under the bowl. When it resonates, each electrode produces an electric current. It depends on the orientation and the oscillation of the bowl placed just above it. In other words, where the bowl oscillates the most, there is more current. And where it oscillates less, the current is very weak. If the electrodes are facing a different direction from the oscillation, then other electrodes will provide the stronger and weaker current. Thus, it is possible to deduce the orientation of the vibration with respect to the electrodes, and finally, the rotation of the bowl.
Do you have an example?
Let's say you have a gyroscope installed on your car. When the electrodes continuously supply the same electric current, this indicates that neither the bowl nor the electrodes have moved relative to the vibration, which is always pointing in the same direction. So your car is driving in a straight line.
Okay. Otherwise, what happens?
When the electrodes produce a different electric current, it means that the bowl and the electrodes have rotated with respect to the vibration. And since this bowl and the electrodes are connected to your car, it means that it has changed direction. Then, from the current delivered by the electrodes, a computer precisely calculates the orientation of the vibration with respect to these electrodes. It then deduces the angle of the rotation of your car. In this case, it is turned 45 degrees to the right.
Got it. And all thanks to a tiny object.
The most amazing thing is the immense precision of this gyroscope, or HRG. The measurement error is much smaller than 1 degree after a week. This gyroscope is therefore perfectly suited for precise navigation. Plus, it's barely bigger than a coffee capsule.
Speaking of coffee, I'm going to the coffee maker.
Now we're going to see how these gyroscopes are manufactured and assembled. And for that, I'm taking you to the Allier department at Montluçon in the Coriolis building, which is entirely dedicated to the production of inertial navigation systems. And you will see it is state-of-the-art technology. Evidently, you've understood it. There is no question of letting in any dust here, so they've created 6,000 square meters of clean rooms where air is filtered and where the temperature, humidity and pressure are controlled.
Son humidité et sa pression sont maîtrisées. Imaginez-vous dans les salles ultra.
Imagine yourself in the ultra-clean rooms in this Coriolis building. There are less than 10 dust particles per cubic meter, whereas in a normal environment, there are billions of them. And now I'm taking you to discover ring laser gyroscope production. Follow me.
Fabrication des gyrolasers. Suivez-moi.
Making a ring laser gyro is a little bit like a cooking recipe. There are several steps to be taken in a precise order and with great care. And it's in the machining hall that it all begins.
So, the machining consists initially in removing as much material as possible from this rough draft shape that you can see on this side, in which we're going to carry out several machining operations, such as milling and contouring with specific tools in order to produce a rough and finished piece. We've removed and carved out as much material as possible from this piece to prepare the following steps.
Presto! After 2 or 3 clicks, the robot takes action. It entrusts the part to this machine equipped with diamond tools, therefore making it very resistant. It is the only material capable of coping with this glass block. What is that watering used for?
The machining process on these very specific materials can only be done by spraying with a particular lubricant, which will be used precisely to evacuate the calories and reduce the friction coefficients at the points of contact between the tool and the element.
Even with this precaution, the process slightly weakens the block, that is to say, accumulates tension. To remove them, the future ring laser gyro soaks for a few minutes in acid baths and then rinses. Once it is finished and relaxed, a bit like when you get out of a bath, it is sent to be polished.
We're going to try to achieve an almost perfect flat surface about a few angstroms. That is a few atoms in reality. The second parameter that we are going to look for is the surface state, which is the topography of the relief that can be distinguished on the surface of a well-defined element. The surface state is also of the order of a few angstroms, in other words, a few atoms.
That's crazy. That's thanks to this great turntable. Look, several gyro lasers are placed on it. The white liquid that you see contains in a mixture of water and microscopic grains in contact with the blocks. This mixture gradually polishes the surface. The process is naturally repeated for each side, and this step cannot be overridden.
Well, this step is critical because the desired details are extremely demanding in order to ensure a surface which is as perfect as possible to allow us to carry out the molecular adhesion mechanism, which will come later in the assembly of our sensor.
Subsequently, the next process happens in these ultra-clean rooms. At this stage, the unit is ready to accommodate the elements that ensure the functioning of the laser. Among them are 3 mirrors made from this glass component. A few layers of atoms from a secret atomic deposit are placed on it to make them reflective. Then they are cleaned and it is made sure that the surface is perfectly flat. It is only after these steps that they are fixed to the block.
These mirrors must absolutely have complete purity on the laser. We cannot glue them with glue or other substances. So we are going to start with molecular adhesion. It is the hydrogen atoms that bind together. As a common example, when you put a wine glass on top of a wet table, it remains stuck. That's it, but taken to the extreme and industrialized.
In addition to the mirrors, the block is equipped with different kinds of electrodes.
The electrodes have a fill tube, which makes it possible to ensure the link between the outside and the inside of the cavity to be filled with gas. The anodes and the cathode generate power and activate gases in the cavity to produce the laser effect.
The electrodes are positioned with utmost precision. The operation of the laser depends on it. It's the same process with the mirrors. This step is called alignment.
The goal is to ensure that the circulation of the laser is continuous and is exactly the same for each round. If we have too much loss in the cavity as the laser travels, we will lose the photons and the laser will eventually stop.
Obviously, it will function less. Once the assembly of the electrodes in the mirrors is completed, the inside of the block is filled with helium-based gas and neon lights.
It's this gas which stimulates the electrodes and which subsequently generates a laser phenomenon. There are several stages of filling tubes. We will completely purify the cavity, and after that, we will be able to fill it up and seal the lasers afterwards and then test their first performances.
The last stage of the manufacturing process consists in connecting the block to an electronic card. This is the measuring information. This time, the ring laser gyro is complete.
Well, we have just left the ultra-clean room. Philippe, generally speaking, the main thing here is to not let in any dust, is that right? However, what if dust comes in?
A dust particle will degrade the performance of the sensor, so that's why we work in an ultra-clean room.
It applies to both the gyro lasers or for the famous HRG, of which we are now going to discover the manufacturing process. So where does it start?
So the first step in this manufacturing will be the machining phase. We will machine both the resonator and then the electrode holder.
So, just as a reminder, the resonator is also called the bowl.
Exactly.
Okay.
After the machining phase, the performance of the resonator is checked and verified that it has the right frequency and that it does not have too much shock in its vibration.
That's this little operation that we see with a laser beam on it.
Exactly.
So the goal, in fact, is to know if it actually works well.
Precisely.
Then what?
So then we will place a very thin layer of metal on the equator, inside the bowl, on the bottom.
Okay.
That makes it conductive. Simultaneously with these operations, we will prepare the electrode holder that will allow us to maintain and capture the vibration of the resonator. The first manufacturing step will be placing a thin layer of metallization.
Okay.
Once we have deposited this thin layer of metallization, we're going to perform an operation called photolitho-engraving, meaning that we're going to deposit a thin layer of photosensitive resin. We're then going to place a mask that will allow us to expose the position of the lights that we want to reveal. Finally, we're going to do an acid attack to be able to reveal the position of its wire.
And that is done in several stages in different products.
In different products that are both acid and rinsing baths to be able to remove all the resin that we want to remove and treat the metal below.
So for the moment, we have two elements ready.
There you have the resonator and the electrode holder. The next step is to assemble these two elements. We're going to assemble the resonator in the middle of the electrode holder. This set is going to be assembled on its base, and we're going to obtain what's called a resonant sub-assembly, ready to measure vibrations and performance. Despite everything, the sensor is not yet efficient, so the next step will be what is called balancing. We're going to make sure that the vibration of the bowl is perfectly uniform over its entire circumference. To obtain that, we're going to remove a few nanometers of material from the mass.
We can see that it's an extremely high-level precision work.
We are really playing with atoms.
What is this little electronic chip here?
This electronic card is what will allow us to start shaping the signals which are sent by the vibration of the resonator, which will then communicate with the external system.
We see that it is also extremely delicate work because we can hardly see the wires laid out.
This is called bonding. We're going to electrically connect the wires by welding two tracks, which are quite close.
Do we have all the elements there?
We do not exactly have all the elements, since the sensor is still sensitive to the external environment. As we have said, the smallest particle that falls on the resonator will degrade its performance.
So we're going to have to put it under the cloche, so to speak.
Yes, we must protect it. That is the purpose of the hood here.
Under this cover, a vacuum is created.
We are going to empty it completely to avoid distortion. The vibration of the resonator will not be affected by the surrounding molecules.
And now we're going to integrate them into the inertial system.
Absolutely.
Eh bien justement, l'intégration, c'est ce qu'on va découvrir.
The integration process is what we're going to discover now. You can imagine that these little jewels of technology will be put to the test when loaded, for example, into a rocket. This is why it's necessary to subject them to a whole series of tests in extreme conditions. Have a look.
Toute une batterie de tests dans des conditions extrêmes. Regardez.
In this workshop, the performance of inertial navigation systems are tested, measured, and corrected. But before that, there is a final assembly step.
We're going to integrate different sub-assemblies to finally seal the boxes in what we call an inertial navigation system. There are the sensors, which are gyrometers and accelerometers that are integrated on mechanical parts to be able to orient them along the three axes. Then, we add electronic cards that manage the system. This will make it possible to manage the power supply of the system and process all the information from these sensors. Actually, we're at the very last production phase before customer delivery.
When the inertial systems are finished, they are installed on these strange machines. They are called two-axis table.
In fact, a two-axis table is a tabletop on which we will have our inertial units. This tabletop rotates around an axis, and then the whole system will rotate on a second axis. By combining the positions of the internal axis of the internal plate and the external axis, we will finally be able to try the product in all the desired positions for a test sequence.
Wow, makes you dizzy. So imagine when they reach several hundred spins per minute. But what's the point of moving the inertial units in all directions?
This two-axis table allows simulating very precise positions and speeds. We create scenarios that ultimately make it possible to determine the errors of our sensors as well as the associated electronics to correct, verify, and then modify them to reach the expected performance.
In addition to being shaken, the inertial system is subjected to large variations in temperature.
Roughly speaking, the temperature range on which we will test its surroundings is -40 degrees to 80 degrees Celsius, variable temperatures to adapt to a wide range of equipments and products. In fact, these are temperatures equivalent to those that the equipment will experience in use. Depending on the products, we're going to apply thermal profiles using ramps, that is constant temperature rising or falling, or we test the units at different temperature levels.
The tests do not end there, since some units endure powerful and repeated shocks. They also undergo significant vibrations to produce real conditions.
Let's take the Ariane rocket at the time of takeoff as an example. The inertial system will undergo a very significant force, and therefore must maintain efficiency at the time of its takeoff. Another example is an inertial navigation mounted on a tank or on a 4x4, which will be on a very bumpy road and which will suddenly be shaken. So when the inertial system experiences this kind of stress, the platform must always be efficient. So we're going to simulate the same kind of mechanical stress on the equipment. This is what is called a vibrating pot.
This test phase lasts an average of 24 hours before the inertial navigation system is delivered to the customer. The inertial system will then encounter real extreme conditions.
Okay, so as this hemispherical resonator gyroscope is particularly efficient and reliable in the most extreme conditions, as well as being very compact, discreet, and truly lightweight, you can imagine that it opens up a wide range of applications. Utilizations in the military field, of course, but also in the civil sector. Watch this.
Whether on land, at sea, or in the air, the HRG already has lots of uses. Note that, with its small compact size, lightweight, and low energy consumption, it is rather well suited to certain machines.
You can imagine that in a submarine, space is limited, and we cannot afford to increase the size of the submarine to fit several devices. Well, with HRG, as it is smaller and lighter, we will gain volume for the same performance, leaving space for other equipment. The same situation in a fighter plane, like the Rafale. If your inertial navigation system reduces in volume, you gain points, meaning that the airplane performance will go above and beyond. Or you can add other devices that enhance the sensor performance.
This tiny 3-centimeter wide gyroscope also opens up possibilities formerly unavailable for land vehicles.
One of the restrictions that we had before was that the inertial navigations were quite heavy and took up a lot of volume. Thus, a little complicated to integrate them on a vehicle like a large 4x4 or a land military vehicle. By reducing the size, you can now install an inertial navigation system on these vehicles and allow these land vehicles to have access to this kind of technology, to inertial navigation, which wasn't always available before.
The HRG equips even more unexpected objects.
When we take portable binoculars in a military environment, and the same goes when we want to observe an animal in the mountain, you have to zoom out, but the image shakes, so you have to stabilize the images. You can't stabilize the inertial system because they're too big. On the other hand, with the HRG, we think that this small capsule can be in portable binoculars with high performances and great stabilization. You can have very high magnifications and an image that seems completely fixed and therefore effortlessly usable, whether it is for animal observation or for infantry.
Let's look up at the sky for the next European Ariane 6 launchers that will be equipped with HRG. This 50-gram HRG will lighten the launchers, and that is crucially important.
Considering weight is critical because the smallest gram, the smallest kilogram on a satellite or a launcher to be put into orbit is absolutely very expensive. Obviously, if you reduce the weight, then it is a tremendous financial saving factor.
In addition, the HRG will more accurately help place the satellites in orbit around the planet.
The more precise you are in setting up at the orbit, the more the satellite will not need to reposition itself during its lifetime, therefore gaining longer service life and durable lifespan. Another example, not only within the military sector, but also in the civil sector, are many satellites known for observation, intelligence, and surveillance capturing images of Earth. You can imagine that the more precise the positioning and stabilization of the satellite are, the more detailed the images captured and extracted from the ground, giving their precise coordinates, will be. So it is very important for the military, but it also allows the general public to access performances that were not accessible to the general public before.
Believe it or not, the HRG is also installed on drones or UAVs, but not just any drones.
In everyone's mind, drones are the ones bought in department stores. Recreational drones do not apply because the cost is too high to take small apps like that, but there is a wide range of drones. For example, there are submarine drones that inspect submarine cables, or 90% of the world telecommunication transit. We have also heard about autonomous cars, but we are also going towards autonomous boats because they're in fact surface drones, and these objects need to be positioned in the absence of satellites. HRG is something ideal for that because it is compact, has low energy consumption, is durable, and is considering the products inexpensive.
In short, you've understood that this gyroscope already provides a lot of services.
So now we're going to talk a little bit about the future. We understood, Emmanuel, that with the HRG, inertial navigation was becoming more and more efficient and also miniaturized. But ultimately, beyond the military applications that we've seen, is that what we really need because we have GPS anyway?
You're right, Fred. Because with radio navigation, American GPS or European Galileo, you can have navigation accuracy down to the meter for a few euros available in smartphones. But radio navigation has a big problem, which is that it can be jammed. So that also means that for a few euros, you can buy an illegal jammer and suddenly drop the whole radio navigation system over a few hundred meters or more, even several kilometers.
As easily as that these days?
Yes, unfortunately. The military GPS is obviously more robust, but regrettably, the civilian GPS can very easily disappear over an entire area.
So it's essentially a question of autonomy in the military domain, but also civil.
In the military domain, autonomy is exactly what we call sovereignty because we are trying to be totally independent of all mapping software, specifically the GPS. And then, in the civilian domain, well, we can imagine new applications, that is, nowadays, new forms of mobility.
For example?
We talk a lot about flying taxis like VTOL that will take you independently and autonomously from point A to point B.
Without a pilot?
Indeed, without a pilot and over cities. We can imagine that these systems need an autonomous navigation system because if their GPS got jammed, their entire system could fail. So we're talking about flying taxis. But we are also talking about delivery drones, allowing packages to be delivered autonomously.
So since we are talking about the future, we can also talk about other ultra-modern state-of-the-art technologies to come.
Exactly. We are talking about ultra-high performance.
Yeah.
Especially on technologies called quantum. So we are actually going to use atom properties to make inertial sensors employing quantum gyrometers and quantum accelerometers.
Concretely, what would that allow?
To have ultra-powerful and significant performances. To have total and complete autonomy and absolute sovereignty in relation to radio navigation. And there, of course, the military field is extremely interested in this type of technology.
But today, when we talk about quantum computers, we know that it takes up a lot of space.
Quantum sensors today operate in the laboratory with extremely remarkable performance and extraordinary high prospects. But they take up a lot of space to be able to take it on board. It would take the entire volume of a 747 cargo plane to make an inertial unit with 3 gyrometers and 3 accelerometers.
Okay, so in principle, we can think about quantum, but it's still not for tomorrow.
Yes, it's not for tomorrow, but it opens up great prospects.
And then in the future, we can also imagine that the electronic elements will be smaller and miniaturized?
Exactly, because the goal of these inertial sensors is to integrate them, make them accessible to as many devices as possible. So today we are developing technologies that are called MEMS, i.e. microelectromechanical systems, which are technologies that originated as microprocessor technology found in your laptop or your cell phone. These technologies not only make it possible to considerably reduce the size of the sensor, but also make it accessible in terms of costs.
And to have them in everyday objects.
Exactly. We are thinking of drones in particular, or other applications of the humanoid-type robots, which would effectively allow autonomy and sufficient navigation without GPS.
Thanks, Emmanuel. Finally, to give you an idea of the progress, well, here is 50 years of inertial evolution. So I hope you enjoyed this report and that it allowed you to discover or rediscover the main principles of inertial navigation systems and its new applications. See you very soon for a future documentary and above all, stay on course. Goodbye.
On garde le cap. Ciao.